Hi there, you're in the lab with your mate JJ. Today is Maxitronix 30in1 day. Today we're going to keep on working through our Maxitronix 30in1, our electronic project lab. My silly job title for today is Systems Architect. Today I'm the Systems Architect, which isn't really so silly a job title after all. I'm sure that there are systems architects out there. Last week we did circuit number 6, which was a transistor for amplification. And this week is circuit number 7, which is the sunrise sunset light. So we're going to jump over the computer, read the instructions. Then we're going to make the circuit in KeyCard. And then we're going to pop over to the booth and assemble our project. And we're going to bring it over to the bench and have a look at it with the multimeter and such. And then we'll wrap up. So let's jump over to the computer and have a look at the instructions.
Alright, so here we are on the computer, and we're going to get the instructions for project number 7. And here we are. So this is circuit 7, the sunrise sunset light. After the circuit is complete, hold the wire to 31 and watch the LED. It will slowly light up like a sunrise. When the LED reaches its brightest point, remove the wire from 31 and the LED will dim and go off like a sunset. If you touch the wire to 41, the LED will go off very quickly. In this circuit, the transistor is used as a switch. It switches on slowly because the 100 microfarad capacitor must be filled up or charged before the electricity can flow through the input of the transistor to turn on the output and the LED. The 100 kilo ohm resistor reduces the amount of electricity flowing in the input circuit, and this makes the capacitor charge more slowly. Touching 41 makes the capacitor discharge very quickly because it makes a short circuit, a path with little or no resistance for the capacitor to empty through. What do you think will happen if you change the values of the resistor or capacitor? Write down your guess and then try changing the resistor to 10K or 470K ohms. Next, try the 10 microfarad capacitor in place of the 100 microfarad capacitor. Note, the 10 microfarad and 100 microfarad capacitors are a special type of a capacitor called electrolytic, and they have a positive and negative connection. Be sure to keep the wiring the same when you switch them, or they could be damaged. Did you get the results you expected when you made the changes? Don't forget to make some notes. So this is the schematic. We've got a switch. Okay. So we've got a 100K resistor, we've got an LED, we've got a 680 ohm resistor, we've got a 100 microfarad electrolytic capacitor and an NPN transistor and 3 volts from the batteries. And this is the wiring sequence, so we'll do that over on the bench. But what I wanted to do now is just make the circuit in KeyCab. Just give me a sec. Okay, so there's our circuit all drawn up. I've drawn it with the switch just wired in on the on position. I'm not sure what we should expect to see if we try and run a simulation, but let's see what happens if we run the simulator, and let's add just DC operating point. I'm not sure if that will. Okay, didn't like that. Edit. Close that. Add. Let's try. I am really not an expert. Time step. 0.01, say. Final time, 1 second. Or let's say 3 seconds. Initial time, max time. Okay. And we should add some points. Save that. Let's add a point here. We want fixed global labels. We'll call this charge. I'm not sure exactly what to expect here, but and let's put one here as well. We'll just call it power. Sorry, these labels aren't super well considered, but basically I want to see if there's electricity flowing through the transistor with power, and I want to see what's happening here with the charging of the capacitor. So maybe we'll see something. I am really not sure what to expect or if we're doing the right thing. Inspect simulator, and we want to show the V charge and V power, and save and run. Okay. Okay, there's no all right, give me a second. Okay, I forgot to set the simulation model on the LED. So double click on that and bring up the properties, and then click simulation model and use a built-in diode. I'm not sure if we can specify the forward voltage here somewhere. I don't know. DC. Forward knee current. Forward bias. It might be forward bias. I'm not sure. If anyone knows, I'd be happy to hear from you. I don't think it's going to be capacitance, not temperature, noise, limiting values, maximum voltage in forward direction, maximum voltage in reverse. Yeah, I don't know. Just a standard diode will probably be okay. So I haven't changed the forward voltage, but it probably doesn't matter much. I think a standard forward voltage for a diode is about 0.6 volts, and the LED is more like about 1.8 volts for a red LED. But I couldn't see the settings, so we'll just leave it as is. Now, hopefully, we'll be able to run our transient analysis, and we did, but it didn't show anything very interesting, did it? So just take a break. Well, I've been playing around with the settings, and setting up a voltage controlled switch is non-trivial, and I tried following some instructions to do it, but I wasn't able to figure it out in the end. So it's probably achievable, but not by me today. So today we're going to leave the schematic as is. We've drawn it up in KiCad. The simulation wasn't successful. So let's go over to the bench and we'll actually build one of these things, and we'll have a look at it on the bench to see how it behaves. All right, so here we are in the booth, and the first thing we're going to do is pull out the old wiring. So let's do that together now. Alright, so all the wires are out, and the next thing to do is just follow the wiring sequence, so let's do that together quickly. Alright, well that's all wired in, so let's take it over to the bench and see how it works. Alright, well here we are on the bench. Now the instructions say to take a wire, this is the wire, and attach it to pin 31, which is on this side of the 100 kilo ohm resistor. So when we do that, we hold it there, nothing, 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 and bang, the LED lights up. So, and then we take it away and the LED slowly goes down, down, down. If we want to speed it up, we can discharge the capacitor just by shorting its terminals, which we do now, and that goes all the way back down to 0. So let's have a look at a few things. First of all, let's grab a trusty multimeter and we'll put it in a DC voltage mode. Oh, there's a millivolt scale. That's good. Let's use that. So we're going to need some banana plugs, I think. So let's just plug that in there. And let's put the multimeter across the LED, and we're looking at about 8 millivolts just from nothing. All right, now if we start to charge him up, okay, it goes, oh, it's actually gone higher than a millivolt. That's interesting. All right. So let's just short him out again. All right, now let's put that on there. Charging, 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 and then it goes up 1.8 volts, and then it should come back down 1.7. You can't see that because of the glare. Sorry about that. How's that? Bit better. So let's just start from scratch. Zero it out, goes down low, and let's charge it up. So we'll see the voltage goes up to 1.8. The LED at this point is completely on. You can see that. And we take the thing away and the LED's brightness diminishes as the voltage starts to drop away slowly. So it's very dim now at 1.6 volts. And yeah, you can almost not see it at 1.6 volts. And if we just press that, it should run all the way to 0, and it does. Okay. So yes. Now I did say to trial it with different different capacitors and different resistors. So let's try with the 10K resistor and see what it does if we wire that in. Okay, so with the 10K resistor, it charged up to full brightness very quickly. Very quickly indeed. So look at that, almost instantaneously at 10K. So we should probably see, if we switch it over to the 400K, we'll probably see that it charges really slowly. So let's see what happens now if we put that on there. Charge, 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 charge. Oh gee, it is real slow. It's happening. Oh, there it goes. Up it comes. Just about 1.6. There we go. Okay. So it did take a while, didn't it, to charge up that capacitor? And while the capacitor is charging, the LED doesn't have any juice. All right, so we'll let it go, and it discharges fairly rapidly, and we just short it out. All right, well, let's switch in the other capacitor. So this is a 10 microfarad capacitor. So this is using the big 400k resistor and the small 10 microfarad capacitor, and it charged up fairly quickly, didn't it? Because it just had to fill up the capacitor, and the capacitor discharges quicker because there's less juice in it. Yes, very good. That all makes sense. So if we put this down to 100k, it'll charge very quickly indeed. So let's put that on there. Yeah, almost instantaneously. Cool. Up we go, off we go. All right, and just for the sake of it, we'll do the 10k, but that'll just be instantaneous as well. On we go, straight away. So the bigger capacitor allows the thing to run for longer. Should we set a timer and time it? I suppose we could do that. All right, so what we're going to do is we'll put it at we'll just put it at 100, which is what it was originally, and we'll charge it up and then see how long it takes to discharge. But I'm not sure actually what we'll use as our metric. So it goes up to 1.8, and if it comes back down, it goes. So let's say when it passes 1.6, when it passes 1.6, that it's discharged. Let's say. So we've got it all charged up at the moment, and we're going to start and disconnect and stop. When it goes below 1.6, we stop. So it was 4.5 seconds. 4.5 seconds. So now let's try the larger capacitor. It's 10 times bigger. And let's see what happens if we do that. So we clock reset. All right. So let's charge him up. All right. So we're all up and take him away. Start, stop. When it goes below 1.6. Oh gee, it's really hanging in there at 1.64, 1.63, 62, 61, and okay, I'm going to call it now. All right, so that went from about 4 seconds to about 28 seconds. So the bigger electrolytic capacity didn't hold it for 10 times as long, but it did hold it pretty long time. So it was basically 4 seconds versus 28 seconds. Fair enough. Now, is there anything else that we would like to see? We could investigate the current draw. I'm not expecting that to be particularly interesting, but let's put this guy in current mode and put it on microamps, and then we'll just intercept the power here. Okay, and let's just see what the current draw is like. The current should probably go on straight away as it begins charging. Yep. Oh, okay, we've got the polarity the wrong way round. So might as well fix that. That's an easy fix.
All right. So just discharge him there. So when we hook the thing in, it starts drawing 26. Oh, that's interesting. So it draws 1.3 milliamps. There's still a little bit of current going through. It's interesting. And if we just short him out, it goes down to 0. Cool. So we checked the voltage, we checked the current. I don't think there's going to be anything to see on the thermals, so I'm not going to turn that on. Did we want to see anything on the scope? I don't think so. I think we know how this works. So from the top, when it's on, the capacitor soaks up all of the energy and doesn't allow anything through the base. But once the capacitor is fully charged, the power can run into the base, and then that turns on the LED. Yes. It's yeah. All right, well, I think that's it. So we'll take you over to the farewell cam, we'll wrap up. Before I take you over to the farewell cam to wrap up, I just want to talk a little bit about what's happening here. It's not being powered by the capacitor. The LED is being powered by the battery. And the capacitor is affecting the current that will flow through the base of the NPN transistor. So what happens when we turn it on through this capacitor, through this 100K resistor, the capacitor begins to charge. And while the capacitor is charging, it sucks all the current out of here into itself, which means that there's no current here. But when it gets about full, then it's not sucking the current away, and the current comes through the transistor. So once this is fully charged, this will turn on and the LED will come on. But it's not the LED, it's not the capacitor that's charging the LED. The LED is being powered by the battery. It's the and so when you take this away, then the power from the capacitor can run back through here and keep the transistor switched on, which keeps the LED on. And if you take the wire and you put it over here, that essentially shorts out the capacitor, which means it'll just drain pretty much instantaneously. And then there won't be any current on the base of the transistor anymore, so the LED will go off. So I hope that's clear, learning about how capacitors work and how they affect the base of an NPN transistor. So with that, I'll take you over the farewell cam, we'll wrap up. And that's a wrap. So that was a pretty easy circuit today called the sunrise sunset light. We used the capacitor to control a transistor. We used the transistor to control an LED. When the capacitor was charging, the LED was mostly off. When it was fully charged, the LED went on. And then the capacitor kept it on even when we removed power from the 100K sort of interfacing resistor. So yes, we continue to learn about electronics. Today learning about the NPN transistor and the electrolytic capacitor. So I think that's everything. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.